So today we're beginning a series on explaining the physics behind nuclear magnetic resonance. So the series won't really be about interpreting spectra, at least not at first. Instead, we're going to explore the spin dynamics that govern NMR at its deepest level. So with that, I have some good news and some bad news. The good news is, like Einstein said, I'll try my best to make it as simple as possible. We'll start from the absolute basics and build our way up, step by step, towards the more advanced ideas. The bad news is that the simplest, honest explanation for why NMR works is rooted in rigorous quantum mechanics, and quantum spin dynamics is not exactly simple. But if our goal is to truly understand the beauty of NMR, then that's something we're going to face head on. So here's what I'll do. First, I'll give you a very oversimplified explanation of NMR, the kind of explanation you'll usually hear in an introductory setting. Then, what will probably become a 40 video series, we'll slowly dismantle that explanation and rebuild it from its first principles. And by the end, hopefully you can come back to this video and see why the simplified story, although useful, doesn't do NMR justice at all. So let's start with that version. So in nuclear magnetic resonance, or NMR for short, we're mainly focused on something called nuclear spin. And this is a property that comes from the nucleus itself. We're talking about the protons and neutrons inside the atom. And somehow, this tiny quantum property ends up telling us an absurd amount of information about molecular structure. What you're seeing here is a bunch of nuclear spins randomly oriented in space. And that randomness is only true when there's no magnetic field present. I want you to keep that in mind. Now, the moment we do turn on a really strong magnetic field, things start to change. Now the spins have preferred orientations. They can either align with the field or they can rebel against it. And by the way, this magnetic field is ridiculously strong. In a real NMR spectrometer, it basically stays on the entire time. Now, depending on which orientation a nucleus adopts, we can either call it spin up or spin down. One problem though, nothing useful is really happening yet. I mean, sure, the spins are aligned, but there's still nothing for us to measure. So we're going to change that by perturbing the system a little. And we do that by using a radio frequency pulse. Basically, a second magnetic field that's much weaker than the main one. Even though it's weaker, it's still strong enough to temporarily knock the spins out of equilibrium. Then once that pulse is gone, the nuclei relax back towards their preferred orientations in the magnetic field. And during that relaxation process, they generate the signal that we detect in NMR. Cool, sounds simple enough. But then we run into another problem. Now, if that was the entire story, NMR would be practically useless. All it would tell us is whether a certain type of nucleus exists in your molecule or not. Basically a yes or no answer, not really helpful at all. The real magic comes from the fact that nuclei in molecules don't all behave identically. Even though they're sitting in the same magnetic field, they don't all feel the same magnetic field. Their surrounding electrons can partially shield them from the external field, so depending on their local chemical environment, some nuclei feel slightly different magnetic fields than others. And that difference is what gives us chemical shift. If a nucleus has lots of electron density around it, it becomes more shielded. If it doesn't, it feels more of the external magnetic field directly. But then another question comes up. What if two atoms are in identical environments? Let's take acetone, for example. That carbonyl carbon right there is unique, but those two methyl carbons are perfectly symmetric. Physics literally cannot distinguish the difference between the left and the right side there. There really isn't a left and right side. So in the spectrum, you get the same signal. You'd see one peak roughly twice the intensity of the other one. Now, another huge thing you'll see in NMR spectra is something called splitting, which comes from what we call J-coupling. But honestly, trying to explain J-coupling right now would be almost criminal. That's one of my favorite phenomena personally, and it's also one of the coolest places where quantum mechanics really starts to show itself. So we'll save that for later. And with that, we've basically described NMR at the surface level. But a good scientific explanation shouldn't end curiosity, it should create new questions. Like, why are some nuclei invisible while other in NMR are? Why do we even need an RF pulse in the first place? How does a magnetic field somehow tilt a quantum object? And even this good one, what exactly is spin? Those are the kind of questions that eventually force us into quantum mechanics, whether we like it or not. So we'll start from the beginning. Atomic structure, the nucleus, and what makes certain atoms behave the way they do in NMR.